and is, if I've got an impulse response, or better, if I have a transfer function, because from an ARMA I got the transfer function, I don't know, s plus 1 divided by s cubed plus s. How can from h of s compute h of t? And now we go to something that you should already know, but let's see where we are there. There is an important mathematical tool that you should already know, that is the one of partial fraction decomposition. Ignore this for now. Ignore this for now. How many of you heard about partial fraction decomposition? I am partially fractally decomposed. I heard about it, but I do not know what it is. Bet or I don't remember very well. Never heard about it. Okay. I think that in Lindsay's you should have been going through a little bit of it. But anyway, we are going to see. So, if I have this object here, this is a polynomial of degree 2. How many s's are going to make this polynomial equal to 0? 2. True? We have 2 roots. That means that I can write this as typically s plus p1, or matter, minus p1, s minus p2 for opportune p1 and p2. True? Perfect. In a certain sense, you should kind of know how to do this stuff here. Whenever we get this one, it's the minus b plus minus square root of 4 b squared minus 4ac divided 2a. This formula here, we know this formula, people. I assume that this formula is known. Perfect. Excellent. Whenever I apply this formula, for this specific case, I get this object here. From this object here, what is P1 and P2? Let's see if you see it immediately. We saw it yesterday. Whenever I get that representation there, s plus 4 squared plus 9. That 9 is a 3 squared. So the roots are going to be minus 4 plus minus j3. People, from this stuff here, this writing to this writing here shall be immediate. Okay? That means that this stuff here, I can rewrite it as, this stuff here, I can rewrite it as, or better, this part here, I can rewrite it as s plus 4 minus, let's make it plus, j3, s plus 4 plus minus, sorry, j3. Okay? Are we together on this? What I reset. Why is this representation very nice? Because I see immediately where I am in the complex plane. Given this writing here, where are going to be the roots? Minus 4 plus minus 3. Okay? And I get the stuff. Together. That means that if I do Laplace, inverse Laplace, now we are going to go. This one is going to correspond to what? This one is going to correspond to E sigma t cosine omega t plus a phase that we do not know and we ignore, okay? And also a number here that we cannot see because we see only the stem. This one is going to be minus 4. This one is going to be 3. Are we together, people? This is another thing that has to come automatically. Those viewpoints and how to write stuff and how to find the roots, etc., 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 has to come automatically. Are we together? Perfect. If I've got this h of s that has got this denominator, that has got this denominator, we already know from the stuff that we were writing that we can write this stuff here as something divided s plus 4 squared plus 3 squared. This is my h of s. The h of t, can the h of t be something looking like this one in time? Yes, no, I do not know. Discuss. Is the question clear? If I have h of s, that is that stuff that I can rewrite in that stuff as 3. Can h of t be an exponential like this? The answer is no, because this one doesn't look like this one. I really want to be clear. Whenever I have in time something that looks like an exponential, this one is going to be something that looks like a cross. True? Something that looks like oscillatory means that I've got something for which I've got imaginary parts. Okay? Together? And indeed, this stuff here corresponds to what? Something that is minus 4 plus minus 3 in the sigma omega part. Okay? And so we should remember this part here. Or better, this one. This one is a bit better representation. Okay. Now, I have this. That means this one. This is the RCL circuit before that I was saying before, with specific R, specific L, specific C. Then those numbers here, we rewrite them in this way here. This one is a 3 squared. Okay. What do I get? I get that I can write it as this part minus this part. This part here is this stuff. This part here is this part. True? And I've got a 1/20th in front and a 4 in front. This one should be wrong. Oh, no, it's correct. It's correct. I think it's wrong. This one should be wrong. I think this one is a 1. No, this one is actually wrong because it should be 4/3. I think it should be for this one should be wrong. I've got an intuition that it's wrong because it's kind of wrong. Somebody sends me an email, Damiano, check. This one is correct. It's like I've got to check. Okay. Anyway, the important part is this one. I take h of s, and I write it as from the ARMA. This one is what I get from the ARMA. Are we together that this is how I write it from the ARMA? Perfect. I write it as, in a certain sense, objects divided by products. I do the partial fraction decomposition. That means something plus something plus something. And this is a operation that you should already know how to do. We are going to go through a little bit in 2 minutes. And then each object that I have shall be in this lookup table of rules for which I know how to invert this object immediately. This is the workflow. How much is the workflow clear? Very much clear, not at all, kind of clear. With an I think I do an example here. Let's do an example here. H of s equals to s plus 3, s squared plus 4s plus 1. Let's see which numbers I get. Let me think at some numbers that are nice for which I can get it. I write it in this way: s plus 2 s plus 3. So it should be 5s and 6. Okay? So let's assume that I've got this one from the ARMA. Okay? Together? Ignore those ones for now. Are we together that we get that stuff from the ARMA? Perfect. Then at this point, I know that this one, I can write it in this way. This is going to be equal to s plus 2, s plus 3 divided, no, let's plus 4. Sorry, I'm kind of creating something on the fly because I don't want to enter into more complicated problems right now. We got this from the ARMA, and I rewrite it in this way. Together? Let's assume for hypothesis that I can write this object here as a divided s plus 2 plus b divided by s plus 3. Okay? Let's assume that I'm able to do this stuff here. Then, if I inverse Laplace this stuff here, what do I get? Laplace minus 1 of a divided s plus 2 is going to be equal to what? Should be a e minus 2t. You got it? You see? And if I have this one, I get this one. True? What is this operation that I did? I took my ARMA. I rewrote it into a sum of objects for which each individual object appears in this lookup table that I told you you've got to memorize, and for which I can do the inverse computation by just looking at the lookup table. Each component will be amplified or diminished by a certain factor, but in a certain sense, a times 1, I rewrite this as sum of objects in the lookup table. And then I inverse Laplace. Are we together on the workflow? Is the workflow clear now? Perfect. And in a certain sense, this is an interesting operation because it's purely algebraic. You've got to know how to do partial fraction decompositions. We are going to do some exercises, so we are going to get on board on there. But that operation is just something that, from a computational perspective, you can do by hand. Computers can do by computers very easily. Okay. This, taking the ARMA in Laplace and do the partial fraction decomposition, computationally speaking, is immediate. From a computer perspective, inverting them is just looking at the memory and applying some lookup tables. This operation, immediate. Okay? Get the point? Tell me.
The example you gave us, the first one, it should be 4 divided by 3, right?
I think so. I think it should be 4 divided by 3. This one should be 4 divided by 3. I think I forgot the 3. Because it's the lookup table, it's this one. Okay. And there I should have gotten s minus 4 plus 4. And then at the bottom, I've got the denominator that is s minus 4. Was it minus 4 plus? Sorry. Yeah, indeed. It would have been unstable. Okay. And then I divide it into s plus 4, the denominator, minus 4, the denominator. This one, I can apply directly this one, and I get this. True? This one, I've got to do it right in this way, minus 4 divided by 3 and 3. And for this part here, I get this one. Are you following me, people? 1, 2, 3. Perfect. At this point, let's connect with something that we were doing before. It's an exercise that we were doing before. I was telling you that if somebody tells you that my h of t from a Laplace perspective, looks like this one. I was telling you, given this plot here, this one, to what shall it correspond? Go, do. Which modes, which atomic elements correspond? Go, do, discuss, and do it. Okay, people, look at me. This is what I get. I get like those two indicate a sign, exponential minus 3, sine 2t, sorry, 2t. This one is a double cross. That means t e minus 5t, because it's on the real line. I got it. I would have gotten it with 2 minutes more. I was lost. Watch out that this thing here of going from the crosses to the exponent to the h of t has to be immediate. Now, if h of t is this stuff here, h of s, how has it to be? H of s has to be the sum of two components, component 1, component 2. True? That's a question. The same. There's a phase. It's the numerator. It's the numerator. Now we are going to go through the stuff here. We go through this stuff here. Wait a minute, and then we arrive at answering this question in a good way. H of s has to be two parts. True? Because there's two objects in a certain sense. True? And this part here, if this one is related to this part here, this one has to be something the numerator divided s minus plus 3 squared plus 2 squared. True? Do you see it? Do you see that this component here has to have this kind of structure as an h of s? Are we together on this? 1, 2, 3. And this part here, this one is component 2, and it has to be something like something on the numerator that we do not see because we do not see from above the numerators. S plus 5 squared, because the squared is two crosses. And from a lookup table, the two crosses, in a certain sense, match. The number, the exponent here matches. How much are we following me, people? Are we together on this? Question.
Let's say you don't have 2 squared the imaginary part just shrinks, so you have a
Sorry, this one.
if you have for example 5 and
So
squared.
it will shrink. It's like would be square root of 5 squared. So
So it will just shrink down.
square root of 5, I think it's bigger than 2.
Yeah.
Yeah, but would be like this. Interesting thing, if this imaginary part goes to 0, what do we get? If this goes to 0, what do we get? We get the 2 crosses here. True? This would become this. See it? You see the square that pops up? If I have, let's go back to the situation before. Yeah?
Is it the s plus 5 square or just s plus 5?
So here it's 2 squared.
No, yeah, in the bottom one.
Here is squared.
Ah.
And I think that I canceled it for canceling out some stuff, but it's square. In this situation, it's squared. Another question.
So the number of crosses for one pair of poles is determined by the degree of the polynomial in the denominator of the first function before partial. But the degree was higher than second order, you see 3 crosses or 1.
So if the degree is 3, we would see 3.
Okay.
If this one was 10, we would see 10.
Okay. And if they had imaginary parts, they would also be spread out.
Indeed. What's out? What's out? If I have this object here, this one becomes? Okay. See? Together. And if it was like this, it would become 3. Okay? Together. Now let's go back. Let's go to a better drawing. This. It means that h of s was first part plus second part. The first part was having a denominator, second part was having a denominator, true? That actually I can write this as d1, d2 whole numerator. Or expanding s plus 3 squared plus 2 squared times s plus 5 squared. Together? Perfect. Now an exercise for you. Numerator, can we say something about the numerator? No, we don't see the numbers for now. Okay, are we together? Later on we will discuss about the numerator better. Exercise for you. I have this situation, 1 minus 1 minus 2 plus 1 plus 2, okay? H of s has to have numerator, denominator, find the denominator. Go. Discuss, do. Are we together? Look at me. This one is s plus 1 squared plus 1 squared. Because there's a minus 1 and there's a plus 1 here. True? Together, this part here. Second part, this part here is s plus 2 squared, because there's a minus 2, plus 2 squared, because there's a plus 2. Together? And if I write this stuff in terms of decomposing things, this has to be written, H has to be writable as something plus something. Okay? Together? Now let's see something very interesting now. And we complete the viewpoint. This object here corresponds to E minus t cosine omega t. From a time perspective, we have a decay ratio that is the E minus t, and we have a cosine omega t. True? This is my sine omega t, sine of t. True? This one is this one in time. This one, does it go down faster or slower? Faster, the same speed. Slower, you do not know. Faster. True? Faster. E minus 2t goes to 0 faster than E minus t. We are together on this. Perfect. Then we have an oscillation. So let's say that it goes like this. And then we have an oscillation. Is the oscillation faster, slower, or the same frequency, or you do not know with respect to this one? Faster, slower, the same, you do not know. It's sine of 2t. True? This is sine of 2t, not sine of t. True? Sine of 2t, the frequency is twice as sine of t. Are we together? This mode is, in a certain sense, something that does like this. This mode, the blue one, is something that does like the blue one. Interesting part, and now we kind of put the things together. We say that whenever I have something like this, h of s is part 1 plus part 2. True? That means h of t is part 1 plus part 2. True? And it's something denominator, something denominator. This one I can do the lookup table, but somehow the numbers are going to pop out. So let's pretend this is a 1.3, and let's pretend this is 1.4, and then we've got something also here. This would mean 1.3 part 1 plus 1.4 part 2. True? Are we together? Are you following me? I'm kind of decomposing h of t in parts as I was doing before, and you get the point that the numerator is going to decide the amplitude of those modes. I have a system that I bought at Biltema. I bring it home. I hammer it, and I measure the output. And I measure something that looks like this in time. I do it a bit better. What am I seeing? This is H. This is the total H. True? This is the total H of t that I'm measuring. And I kind of see that this total H of t is this, drawn in a bad way, plus this. True? Do you see that the total one that is red is the blue one plus the violet one? True? Where is the blue one from a Laplace perspective? Decay ratio slow, oscillation slow. This one. Let's make it in blue so that we are consistent. This one, decay factor fast, oscillation fast. Where do you have to arrive? Where is where I want you to be at the end of the course? That you see this stuff here and you imagine this stuff here. Because you kind of understand by looking at the crosses how the h of t might look like. And of course, you might have this vibration bigger or smaller, and this initial condition bigger or smaller, depending on the numerators associated to this part. True? Because they will expand things. True? But already you kind of have an intuition of how stuff might look like. How much are we together, people? 1, 2, 3. Very much together, not at all, kind of. Let's do an exercise, and then we do a pause. Or shall we do a pause? Pause.